How does your body just know when to feel energized or sleepy or hungry? It feels totally automatic, right? But behind the scenes, there's this constant storm of messages flying around, a biological wireless network that's running 24/7. Well, in this explainer, we're going to tap into that network and decode the secret messages of the endocrine system.
And to really get this network, you've got to start with its messengers, the hormones. The name itself is the first clue. It comes from the Greek word hormon, which literally means to set in motion. And that's exactly what they do. They are the body's action starters, the chemical signals that kickstart pretty much everything. So here's the game plan. We're going to follow the life of a single hormonal message from start to finish. We'll start with the network itself, see how these incredible messengers evolved, watch them get created and sent out, see how they travel through the bloodstream, how they deliver their message, and finally, how the whole system knows the job is done.
You know, unlike your nervous system with its neat and tidy nerves, or your circulatory system with its veins and arteries, the endocrine system doesn't really have any physical borders. It's this decentralized network of glands and messengers, all working together for one main goal, maintaining what we call homeostasis. Just think of it as the body's constant effort to keep you in that perfect, just right zone, no matter what's going on. So, who exactly are these messengers? Well, they didn't just pop up overnight. I mean, think about it. As life on Earth got more and more complex, going from single cells to, well, us, the job of staying in balance got way, way harder. Hormones had to evolve right alongside life itself, becoming more diverse and specialized to handle everything from stress to growth. Okay, so if you break them down chemically, these messengers fall into three main families. You've got the peptides, and these are by far the most common type. Then the amines and the steroids. And this is where it gets really clever, because their basic chemical structure determines their entire mission. And this right here is the fundamental split in how they operate. On one side, you have water-loving hormones, like peptides. They dissolve and travel easily in the blood, but they can't get through a cell's fatty membrane, so they act like they're ringing the doorbell. They bind it to a receptor on the outside of the cell, which then kicks off a chain reaction on the inside. But on the other side, you've got water-fearing hormones, like steroids. They need a special ride to get through the blood, but once they arrive at their target, they have an all-access pass. They can slip right inside the cell and give their orders directly. This one difference, it changes everything. All right, so we know the different types of messages, but how does the body actually, write them? The process for crafting and sending these signals is just remarkably precise. For peptide hormones, it's this really cool three-step process, almost like drafting and sending an official memo. First, the cell makes this long, inactive prohormone. Think of it as the rough draft. It has the core message, but it's not ready to go. Next, specific enzymes act like little editors, precisely cutting out all the unnecessary parts to create the final active hormone. Only then is this polished, final message released from the cell. Now, you might think the body just releases a nice, steady stream of hormones, right? Nope. The reality is so much more sophisticated. Many of them are released in these rhythmic pulses or bursts. And this means the pattern of the signal, the timing, the frequency, can carry just as much information as the hormone itself. It's really not just what you say, it's how you say it. Okay, the message is sent. Now it has to navigate the body's superhighway, the bloodstream. And believe me, this journey is far from simple. How a hormone travels actually determines whether it can even complete its mission. This is especially true for steroid hormones. I mean, just look at this. You'd think all the hormone in your blood is doing something, but it's not. A staggering 99% of it is bound to carrier proteins, which makes it totally inactive. It's just a reserve. It's only that tiny, free 1% that's actually biologically active and able to get the job done. Almost all of it is just sitting on the bench, waiting to be called into the game. So these carrier proteins, they're not just taxis. They're more like bodyguards and managers all rolled into one. They create a huge reservoir, they protect the hormone from breaking down too quickly, and most critically, they give the body this amazing extra layer of control. By managing the managers, the body can fine-tune exactly how much active hormone is available at any given moment. It's brilliant. So, our message has been created, it's been sent, and it has traveled all the way to its destination. Now for the main event. How does it actually deliver its instructions to the target cell? This is where the message is finally read.
And we're right back to that crucial split we talked about. The water-soluble hormones, they bind to the outside of the cell. It's kind of like a runner in a relay race, handing off the baton. The message is passed along inside. But the hydrophobic hormones like steroids? Oh no, they don't hand off the message. They walk right into the cell's command center, the nucleus, and directly alter the genetic blueprint, telling genes when to turn on or off. One changes the cell's immediate activity, the other literally rewrites its instructions.
So, the message is delivered, the job gets done. But how does the system know when to stop? How does it avoid sending way too many signals and throwing everything off? Well, this is the final and maybe the most brilliant part of the entire system, the feedback loop. It's the message received confirmation that keeps everything perfectly in check. Now, there are two kinds. You've got positive feedback, which is pretty rare. It amplifies a signal to push towards some big finale like during childbirth. But the absolute cornerstone of endocrine control, the system's default setting, is negative feedback. This is a mechanism that actually dampens or shuts off the original signal. It's the body's thermostat, constantly working to maintain that perfect, steady state of balance.
Here's a classic example, and it's super simple when you break it down. The pituitary gland tells the thyroid to get to work. The thyroid does its job and releases its hormone into the blood. Now, once the pituitary senses that there's enough of that hormone circulating around, it just stops sending the work signal. It's this beautiful, self-regulating loop. The final product effectively turns off its own on switch, making sure everything stays in perfect balance.
You know, when you step back and look at the whole thing, this incredible network of messengers, signals, and feedback loops, it's a true masterclass in biological engineering, and it's all designed for one thing: balance. It makes you realize just how delicate this system is, which really leads to the final critical question. In a network this precise, what happens when just a single message goes wrong?